Victoria, in southeastern Australia, was once a land of deep calm. For millions of years it rested peacefully as part of the supercontinent Gondwana. No eruptions, no earthquakes, just stable ancient land. But deep below, powerful forces were quietly building. Soon, this peaceful land would be transformed by volcanic eruptions. The calm before the storm set the stage for Victoria's fiery future. The peaceful era in Victoria ended with the breakup of Gondwana. This massive supercontinent began to split apart around 100 million years ago. The process was slow but powerful, as tectonic forces pulled the land in different directions. As Gondwana broke apart, Australia started to drift away from Antarctica and Zealandia. This movement caused the crust beneath Victoria to stretch and thin. When the crust thins, it reduces the pressure on the hot mantle rock below. This is similar to taking the lid off a pressure cooker. The mantle rock, now under less pressure, begins to melt. This process is known as decompression melting. It was this melting that eventually led to the formation of magma, the molten rock that fuels volcanic eruptions. The breakup of Gondwana was a major trigger for volcanic activity in Victoria. It marked the beginning of a new geological era for the region. As the land continued to shift and change, the first eruptions began. These eruptions were part of what is now known as the Older Volcanics Province. Understanding the breakup of Gondwana helps us see why Victoria's volcanic activity started. It wasn't just a random event. It was the result of massive, slow-moving changes deep within the Earth. This geological shift laid the groundwork for the fiery eruptions that would follow. Initially, scientists thought that a hotspot might be responsible for Victoria's volcanic activity. Hotspots are places where hot mantle plumes rise to the Earth's surface, causing volcanic eruptions. The Hawaiian Islands are a famous example of hotspot volcanism. However, this theory did not fit well with what was observed in Victoria. The main issue with the hotspot theory was the lack of a clear age progression in the volcanic sites. In a typical hotspot scenario, as a tectonic plate moves over a fixed hotspot, a chain of volcanoes forms, each younger than the one before it. This was not the case in Victoria. The volcanic sites did not show a neat, orderly progression of ages. Moreover, the chemistry of the lava in Victoria did not match what would be expected from a deep, uniform mantle plume. The lava's composition varied significantly, suggesting it came from different parts of the mantle. These inconsistencies led scientists to look for alternative explanations for Victoria's volcanic activity. Rejecting the hotspot theory was an important step in understanding Victoria's volcanic history. It pushed scientists to explore other possibilities and ultimately led to a more accurate explanation of the region's volcanic activity. This process of scientific inquiry and discovery is at the heart of how we learn about our planet. The rejection of the hotspot theory led scientists to propose a new explanation: edge-driven convection. This process involves slow, swirling currents in the upper mantle. These currents occur at the boundary between thick, old crust and thinner, new crust. In Victoria, these currents cause localized pockets of the mantle to melt, leading to volcanic eruptions. Edge-driven convection explains the sporadic nature of Victoria's volcanic activity. Unlike a hotspot, which creates a continuous chain of volcanoes, edge-driven convection results in eruptions that are spread out over time and space. This matches the pattern observed in Victoria, where volcanic activity occurred in pulses over millions of years. The varied chemistry of the lava also supports the edge-driven convection theory. As the mantle melted in different places, it produced magma with different compositions. This variability is a hallmark of edge-driven convection and helps explain the diverse volcanic features in Victoria. Understanding edge-driven convection provides a clearer picture of why Victoria's volcanic eruptions occurred. It highlights the complex interactions between the Earth's crust and mantle that drive volcanic activity. This insight helps us appreciate the dynamic nature of our planet and the forces that shape its surface. The volcanic eruptions in Victoria were quite different from the explosive eruptions often associated with volcanoes. Instead, they were generally quiet and effusive. This means that the lava oozed out slowly rather than exploding violently. The eruptions created basaltic lava flows, small cinder cones, and extensive lava fields. These eruptions were not continuous, but occurred in pulses over a long period. From approximately 95 million to 18 million years ago, volcanic activity would start and stop, sometimes with long periods of quiet in between. This sporadic activity was a result of the edge-driven convection process beneath the surface. The basaltic lava flows that resulted from these eruptions are a key feature of Victoria's volcanic landscape. Basalt is a dark, dense rock that forms when lava cools and solidifies. Over millions of years, these flows have created a unique and varied terrain, with rolling hills and flat plains. The nature of these eruptions has left a lasting mark on Victoria's landscape. The quiet, steady flow of lava has shaped the region in ways that are still visible today. Understanding the nature of these eruptions helps us appreciate the geological history of Victoria and the forces that have shaped its land. Victoria is home to several key volcanic sites, each with its own history. One of the most notable is the Pentland Hills Volcanic Group, located near Bacchus Marsh. This group erupted between 66 and 33.9 million years ago, creating a landscape of rolling hills and volcanic rock. Another significant site is the Greensboro Basalt, found around the Melbourne area. This basalt erupted between 23 and 20 million years ago and is visible in places like Watsonia and Kangaroo Ground. The lava flows from this period have shaped the local terrain, creating a distinctive landscape. The Talmarine Basalt, which erupted between 23 and 16 million years ago, is another important site. It stretches from Melbourne's central business district to the airport. The Maribyrnong River has cut through these lava flows, revealing layers of volcanic rock that tell the story of past eruptions. These volcanic sites offer a glimpse into Victoria's geological past. Each one represents a different chapter in the region's volcanic history, shaped by the forces of edge-driven convection. Exploring these sites helps us understand the scale and impact of volcanic activity in Victoria. The volcanic activity in Victoria is closely linked to the formation of new oceans. As Gondwana broke apart, the seafloor began to spread, creating new oceanic crust. This process led to the birth of the Tasman Sea and the Southern Ocean. Seafloor spreading in the Tasman Sea started around 83 million years ago, while the Southern Ocean formed a few million years later. The creation of these oceans was a direct result of the tectonic forces that also caused volcanic activity in Victoria. As the continents drifted apart, the Earth's crust was stretched and thinned, leading to both seafloor spreading and volcanic eruptions. This connection highlights the interconnected nature of geological processes. The formation of the Tasman Sea and the Southern Ocean was a major event in Earth's history. It reshaped the continents and created new environments for life to evolve. The volcanic activity in Victoria is a part of this larger story, illustrating the dynamic changes that have shaped our planet. Understanding the connection between Victoria's volcanoes and ocean formation helps us see the bigger picture of Earth's geological history. It reminds us that the land and sea are interconnected, shaped by the same forces that drive the Earth's dynamic processes. After the older volcanics ended around 18 million years ago, Victoria experienced a period of volcanic dormancy. This quiet period lasted until about 6 million years ago, when a new phase of volcanic activity began. This phase is known as the Newer Volcanics Province, and includes features like Mount Napier and Mount Eccles. The Newer Volcanics Province is characterized by more recent eruptions, some occurring just a few thousand years ago. These eruptions were also generally effusive, producing basaltic lava flows and creating features like volcanic cones and craters. The province is a testament to the ongoing geological activity in Victoria. Today, Victoria is considered volcanically dormant, not extinct. This means that while there is currently no active volcanic activity, the potential for future eruptions remains. Seismic studies have shown that the mantle beneath western Victoria is still hot and soft, indicating that the volcanic system may still be active deep below. The Newer Volcanics Province is a reminder that Victoria's volcanic story is not yet over. The region's geological history continues to unfold, shaped by the same forces that have driven volcanic activity for millions of years. Understanding this history helps us prepare for the possibility of future eruptions. Despite the current dormancy, there are signs that volcanic activity may still be present beneath Victoria. Seismic studies have detected low-velocity zones in the mantle, indicating areas of hotter, softer rock. These zones suggest that the mantle is still capable of producing magma, which could lead to future eruptions. Additionally, carbon dioxide seeps from mineral springs in the region. This gas is often associated with volcanic activity, as it is released from magma deep within the Earth. The presence of carbon dioxide indicates that the volcanic system that began millions of years ago may still be active at depth. The potential for future volcanic activity has important implications for Victoria. While eruptions are not imminent, understanding the region's volcanic history helps scientists monitor and prepare for possible events. It also highlights the need for continued research and monitoring to better understand the risks and impacts of future eruptions. The story of Victoria's volcanic past is a fascinating tale of geological change and transformation. It reminds us of the dynamic nature of our planet and the forces that continue to shape its surface. As we look to the future, understanding this history helps us appreciate the complexity and beauty of the Earth.